All right, ladies and gentlemen, we are currently recording. So, we are about to get started on our next unit, and that unit deals with energy. Energy is not a new concept. We have definitely talked about energy in this class before. Okay? But we're going to expand that definition of energy a little bit more, look at a couple other types of energy, and see how it applies to things that are a little bit bigger. We've talked about energy from the sense of like atoms and bonds before. We're going to talk about some things that are a little bit bigger, a little bit more what we deal with on an everyday basis. So, we are going to start on the set of slides that says energy and energy types. That's where we begin today. So, first, one thing to keep in mind. This idea, this concept of energy, comes from the same place that the concept of force and acceleration come from, in the fact that we're trying to explain why things happen. We're trying to explain what happens in a certain situation and how we know what's going to happen next. Right? Why is it when this object starts up at the top and I let it go that it falls downward, and as it falls downward it gets faster and faster and faster and faster? Why does that happen, or how does it happen? And that's really what we're going to be dealing with when we deal with energy. All the pictures up here are different types of energy, but they all come back to one main concept. Like I said, energy is not a new concept. It's something we've dealt with before. What did we say energy was? What's our definition of energy? The ability to do stuff, or the ability to do damage, or the ability to, the ability to move or change matter. The ability to make things different than they were before. That's what our definition of energy is, right? It's a way of explaining change. Just like forces are a way of explaining change in motion, energy is a way of explaining change in a broader sense. Not just the change in the motion of something, but also in the other changes that we might experience. Okay? The SI unit for energy is joules. It's a capital J. Joules is not a base unit. It is a derived unit. It is a combination of units. Specifically, it is a combination of kilograms times meters over seconds. So if you take kg times m over s, that's the equivalent of what a joule is.
Is the thing that says ability to blank other objects, is that
move or change? Yeah, move or change other objects, or move or change matter.
Did you play for that's aptitude?
Part of the presentation. Probably just the fact that the wind is blowing really hard outside. All right, are we good on what energy is?
Yeah.
The ability to do damage.
Let's start here. Mechanical energy. Mechanical energy is what we're going to deal with most often over the next week and a half or so. As far as a broad definition, energy associated with the motion and position of everyday objects. So we talk about where things are and what they're doing. Those questions seem familiar, I hope, right? Those are the questions we were basically trying to answer at the beginning of this physics unit. Like I said, energy deals with a lot of the same concepts that we dealt with in mechanics. And we talked about explaining those things. Mechanical energy is actually a combination of three specific types of energy. And those types of energy are, first, kinetic energy, which we represent by Ke. Second, potential energy, gravitational potential energy, which we represent with PEG for potential energy gravitational, and then elastic potential energy, which we represent as PEE. Yes, it says P up on the board. Okay, so let's just get that out there now so we can all laugh. It says P, right there, P. It's in capital letters too. So awesome. It's funny. So. mechanical energy is the sum of all those different types. And we'll talk about these types in more detail in a couple of minutes. All right, we go with mechanical energy? Next. Next type of energy we talk about is thermal energy. Okay? We've talked about this idea of thermal energy a little bit before. When things get hot, what do we know that they do? What happens to the particles that make them up?
Faster.
They move faster. Right? So thermal energy is an energy associated with motion, but it's the energy associated with the motion of microscopic particles, the atoms or molecules that make up whatever substance we're dealing with. And hopefully we remember, back to our original discussion, if those particles move more, they have more thermal energy, which generally equates to what? A higher what? Temperature. And if those particles move less, that means there's less thermal energy, less ability to do damage. Has anybody ever had a steam burn before? Like not hot water, but like steam actually burns you?
No.
It hurts a lot. Okay? It hurts more than just like if you get splashed by some hot water from the sink or whatever. Because what do you know about the motion of those water molecules when they are in steam form? How fast are they going? They're going really fast, and as a result, they have more ability to change things, to do damage, to make them different than before. Okay? Great, go ahead. You can. You have to be careful. Now, generally, Miriam, what we think of as steam isn't actually gas water. Okay? When you see, like, steam, that water has already condensed out of the gas phase and back into the water phase. Steam itself, remember we talked about the gases, you can't really see gases because the particles are so spread out. Like if you have a teapot at home, one that you put on the stove, if you let it go until it whistles, you'll see that there is a little gap between like the spout of the teapot and where you actually see like the cloud of steam, because at the very beginning when that water is still in a gas phase, you actually can't see it. It's not until it condenses back into a hot liquid that you actually see the drops. Okay. Does that make sense? But Miriam, the point being though, the sauna definitely can't hurt you if you're not careful with it.
What does back to the other side? What does P mean again?
PE stands for potential energy, and then if it has the G after it, that means gravitational potential energy, and if it has the E after it, that means elastic potential energy. And Sam, we'll talk about those in more detail in a little bit. Okay, that's not the first time we're going to see the first one. All right, there, and come on. Next kind of energy, chemical energy. We've talked about chemical energy a lot when we talked about like making bonds and breaking bonds, and we said that bonding is basically an energy process. That things tend towards lower energy, and if they bond, that means a lot of times they give off energy, blah, blah, blah. Okay? Chemical energy is energy stored in the bonds of a compound. And by making those bonds and or breaking those bonds, we can then use that energy to do stuff. We can use that energy to make things different. As in, we can use it to make you walk from one class to the next class. Or we can use it to make a car go from the garage to wherever it's going to. Okay? Examples of chemical energy, the one that you're most familiar with is food. So your body takes whatever you ate this morning for breakfast. Okay? Omelets.
Yeah.
Man, somebody in the other class had pancakes. Like, what time do you guys get up?
It's my mom that makes
Yeah.
it. I'm just gonna.
Did she arrange like tomato wedges and a smiley face for you?
I hate tomatoes, so probably not.
Anyway.
Actually, her omelets are what?
I just want you to know that's out there for the world to hear.
Oh.
So, sorry, Mom. Still love you though. No, I had Honey Nut Cheerios and blueberry yogurt. So,
That sounds
I'm fighting my cholesterol.
I like putting my Cheerios in my yogurt.
I like to put granola in yogurt.
And fruit.
Fruit too, yes.
It's like a leaf break for my.
Yeah, we actually bought a pineapple last night at the store, but and my wife cut it up. I didn't have to.
Do you have a pineapple cutter? My mom has
No,
special
she
things
used
so
it.
easy.
You know, pineapple's actually really good for Hawaii.
Bagel
Yeah,
cutter.
Next, electrical energy. Electrical energy, by definition, energy associated with electrical charges. From an electrical charge standpoint, what do we know like charges are looking to do to each other? Repel. And opposite charges are looking to attract one another. And we can use that fact to make things different than they were before. This is basically how any electronic device works. It takes advantage of the fact that the electrons in there are repelling other electrons and being attracted to protons, and it causes them to then do stuff. Okay? This is electricity. Okay? Well, here, like an electric motor, okay, whether it's on a hybrid car or whether it's like, I don't know, in one of those little wine, or not a little wine toy isn't a good idea, but like an electric motor, okay? Basically, there's a magnet in it, and that magnet spins, and it spins because there's other magnets that get repelled and attracts it and kind of spins it around like that. That's how an electric motor basically works. There is some stuff in there, like your iPod has electrons that run through it. And as it runs through your iPod, it interacts with other electrons that are there and repels, and then it moves here. But as it moves, it takes information with it, and that's kind of how your iPod works. That's a real sketchy definition. So, but anyway, it has electrons basically moving through it. Anything that's electrical goes. All right. Next. Not to be confused, but electromagnetic energy. Okay. We talk about electrical energy for electromagnetic energy. Electromagnetic energy is energy that travels through space as waves. Now, when we say space, that doesn't necessarily mean outer space. Okay? That basically means any area. Okay?
Like this.
Like this space, yes. You ready? Here we go. Electromagnetic energy. Here we go. Ready? There it is.
You turn the lights on, by the way, folks at home.
Did it make thank you for narrating.
Well, I mean, they can't see the
That's true.
lights.
Did that cause a change?
It kind of hurt my brain.
Kind of hurt your brain, yeah, because your eye reacts to that energy, right? Rods and cones and all that good stuff that are in your eye, right? That light has the ability to cause a change. Okay?
Please.
Easy. You should be bright and sunshiny because you had an omelet this morning for breakfast.
Well, it was a bad one. Like, my mom isn't good at making that.
But you still love it.
Yes. I still love her.
So, when we talk about electromagnetic energy, we're talking about waves that travel through space. Like I said, it doesn't necessarily mean outer space. Okay? Other types of electromagnetic energy. So we just talked about visible light. Okay? X-rays. X-rays have the ability to cause damage, to make things different than they were before. Absolutely. When you go to the dentist's office or when you go to the doctor and you get an X-ray, where does the little X-ray tech lady go? She goes behind a lead wall.
And I like how
I mean, they give you an apron, so, you know. But, Sam, the point being, you get exposed to those X-rays, once every year, whereas she's doing 8 exams a day.
Yeah.
All right?
she is a lot more.
Yeah, she gets exposed to
What will that do?
its ability. So, Grace, its ability to cause change. That's what energy is, to make things different. The one thing that we worry about with radiation or this kind of energy answering Grace's question. You're sitting there talking right in her face. So, Grace, the one thing that we worry about is that that energy goes in and makes something different, that something necessarily being your DNA that's in your cells.
So mutated.
Right. That it causes a mutation in your DNA, and remember, like, DNA is like the blueprint for making a new cell, right? Okay. So now, if you change the DNA, the cell makes something different than it was before because its blueprint has changed. Does that make sense?
When you're pregnant, are you not allowed to get a...
But let's do this. Go ahead. Go ahead, Grace. So if that keeps happening, now, like, whatever. Well, it could, because now, like, the stuff that was in your skin cells, right, they're not making skin cells anymore because the blueprint to make a skin cell has been changed. So now it makes something else. And that's what cancer is. Cancer is your body is just making new cells, but they're not the right kind of cells.
Oh.
And that's why, you know, your body doesn't work right if you have cancer, because it's not making what it's supposed to be making. Does that make sense?
Like, did anybody see the TV show 24 when it was on? Yeah. Some Russian guy, like, radiation, like, his own son, and he kind of, like, saw it.
Yeah. Now, Grace, if you talk about it in, like, terms of really strong radiation, if there's a lot of energy, it can actually kill those cells, which is basically what a sunburn is. That radiation from the sun, the energy from the sun has come and it has changed your skin. It basically hurts your skin. Does that make sense? Yeah. Which is also why you have to worry about, if you have too much sun, we worry about cancer, because that radiation, if it doesn't necessarily kill the cells, it can make them different than they were before, and that's where skin cancer comes in and all that kind of stuff. Okay? So, but it all comes back, right, to our original definition of energy, the ability to change stuff, the ability to make it different than it was before. Very good, go ahead. I mean, from that standpoint, sure, but they have other issues going on as well.
What are the other issues?
I mean, you know, a barn could fall on us. Not many of you are in danger of having a barn fall on you, but honestly, would you know, be more. So.
Wasn't there an old Amish person that was, like, electrocuted?
Like, you know, riding a buggy and things like that.
Because I think he was riding, like, a
Buggy accident.
Yeah, it's not good. All right, last type of energy that at least we talked about for this section here deals with nuclear energy. Hopefully, you remember when we talk about atomic structure. Okay? In the nucleus of an atom, what's in the nucleus of an atom? Protons and neutrons. All of those protons have what charge? Positive. So what are they all trying to do to each other? Repel. The nucleus of an atom is a pretty unstable place, unless there's something there to hold all of them together. We talked about that idea of the strong nuclear force, right? Does that sound familiar from when we were talking about that? Okay. But eventually, if the strong nuclear force isn't strong enough to hold all the protons together, what starts happening to the nucleus? It starts breaking apart. It starts moving apart. And that's what we refer to as radiation, right? Energy being given off in order to make things different. Right? If you get enough of those atoms falling apart, right? If you get enough of those atoms where the strong nuclear force is overcome, and the nucleus starts falling apart, it releases lots of energy. And we refer to that as a nuclear bomb. Okay? Does a nuclear bomb release enough energy to make things different?
Yes.
Yeah, it does. All right? That's the people in Japan. So.
We watched
you said the radiation, like over in the nuclear part, like
Right.
what's the
Radiation is generically a term for a release of energy from an atom. Okay? So, Caroline, the previous part, the electromagnetic part, it's energy released from an atom, but in a different way than this. Okay? In the electromagnetic part, it's more electrons jumping up and falling back down. Does that sound familiar?
Yeah.
That's more where electromagnetic radiation comes from. Whereas nuclear energy, the radiation from nuclear energy comes from the nucleus falling apart.
Oh.
So it's a matter of where is this generically energy coming from an atom? Where is it coming from? Is it more of an electron thing or is it more of a nucleus thing?
Okay.
But the end result is it's still energy. And Grace, like we talked about, energy is the ability to make things what? Change or different. Good. Good there? Oh, there we go. We're still done yet, though.
We finished this.
We did finish the whole.
What is he eating?
There's a pie.
What?
You ever have, like, especially McDonald's pie, they sometimes have it on the box, it says caution and filling may be hot.
Yeah.
Like, you bite into something, it's not
Like it's not on like the outside. It's not hot, but on
right,
the
exactly.
inside.
And we'll talk about that.
Because
Yeah.
kill.
Yeah. It might as well just be lava inside it.
It really
So,
I don't like it when it's stinky.
you know what else is like that? My wife's grandma, she used to make these baked beans. And like they would stay hot, I swear, like for 3 hours. Like dinner would be over for an hour and the baked beans were still like.
Yesterday I went to Aladdin and there's this little roll and it felt like cold on the outside, but I took a bite in it and it was really hot in my eyes.
Yeah.
That was so good.
All right. Easy. But hey,
You guys got fish.
damage, right? It caused damage.
Yeah.
Is that why my mom told me not to stand by the microwave outlet?
Yeah, although, yeah, it's not.
But they have radiation.
Don't worry about
Am I
it.
really
supposed to stand?
Quite honestly, don't worry about it. There's a lot of other things that you should worry about before standing by the microwave.
I only have to find those all for that. Is it shooting your phone?
All right. So, the second set of slides that I gave you today deals with mechanical energy. Yeah. So, first, the second set of slides I gave you today deals with mechanical energy. The beginning of it is review. This is exactly the same we just wrote down, right? So, Grace, like we just talked about, energy, the ability to do stuff, right? The ability to make things different, the ability to cause change. Okay? And we also talked about mechanical energy. So we said that mechanical energy, and Kirsten, this you just wrote down too, but I think it's on your slide at the same time as well. So mechanical energy is the energy associated with the motion and position of everyday objects. So we're worried about where they are and what they're doing. And what kind of damage can they cause because of where they are and what they're doing. That's what mechanical energy is. We talked about that mechanical energy is actually a combination of 3 things, right? Do you remember what the 3 things are?
Kinetic, potential, and potential.
Potential
elastic.
energy, gravitational.
There are 3 kinds of energy. First, kinetic energy, then gravitational potential energy,
And then elastic.
and then elastic potential energy, which shows up like this. Okay? Somebody asked before in the previous slideshow, the G and the E weren't subscripted. It doesn't matter. As long as you can tell them
I
apart.
kind of like it better so.
They're supposed to be. I think I just forgot to subscript them in the previous. You can if you want to. But mechanical energy deals with big things, big objects, at least in the grand scheme of things. We're not really talking about atoms and molecules here. We're talking more like, cars and trucks and balls and you running around. Okay? All right. Are we good with what mechanical energy is by definition? All right. Let's start looking at these specific types of mechanical energy. Now, let's start off with kinetic energy. I'm assuming that most of you have heard of kinetic energy before.
Yeah, but I've never really understood.
Okay, well, let's talk about it.
Teach us.
So, kinetic energy by definition, we say that kinetic energy is energy of what?
Motion.
Motion, right? Sam, because something is moving, it has the ability to change stuff. Okay? This ball doesn't have the ability to change anything until I make it do what?
Move it.
until I make it start going, right? So it's energy of motion. By virtue of the fact that something is moving, it can make things different than they were before. Okay? Kinetic energy depends on two things. It depends on the mass of the object, and it depends on its speed. And you'll notice that in the formula, there's the formula, right? KE is equal to 1/2 mv squared. The formula says v. I've told you speed. We'll talk about why in just a second. Someone asked before about the 1/2. Why is the 1/2 in there? And the answer is, it just is. It's like that's what we see when we measure how much energy this object has versus that object has.
Mass times velocity.
Yep, mass times velocity, but the important part being saying that the velocity is squared. All right, are we good there? So let's talk about these factors. Okay. If we double the mass of the object, if we take a car and then we get a car that's twice as big, they're both traveling at 30 miles per hour. First off, which one is going to have more kinetic energy, the light car or the heavier car? Heavier car. It's going to cause more damage if it runs into something. Okay? How much more damage? Well, if you look at the formula, KE equals 1/2 mv squared, are we doing anything mathematically to the m in that formula?
Yeah. Wait, no, you're doubling.
Well, you're doubling it, right? But Nick, is there anything else that you're doing to the m in that formula? So if you double the mass, how much energy does it have? Double the amount of energy. Okay? That mass is a direct relationship with energy. So if you increase the mass, if you double the mass, you'll have twice as much energy. If you triple the mass, you'll have 3 times as much energy, or you'll cause 3 times as much damage. Okay? However, let's say there's a car in a parking lot and it's traveling 10 miles per hour. Then, a little bit later on, it's traveling somewhere 20 miles per hour. What have we done to the speed of that object? We increased it by what factor, Allison? Twice. It's twice as big, right? But if that object in the parking lot that was going 10 miles per hour runs into a car and it dents the fender, when it's going 20 miles per hour, how bad of a crash is it going to be? Worse. Is it twice as bad? No, it's actually how bad? 4 times as bad. Because what are we doing to velocity in that formula? You're squaring, right? So a 10 mile per hour crash in the parking lot versus a 30 mile per hour crash out there on the road, right? Is it 3 times as bad of a crash? No. Not 4 times. If we go from 10 to 30, right? What did we say we were doing to velocity? Squaring it. So now we've increased the velocity from 1 to 3, so it's what? Not 1/9, it's 9 times as much, right? Because velocity is squared in that formula, right? So if I double the velocity, I have 4 times as much kinetic energy. If I triple the velocity, I have 9 times as much kinetic energy. Okay? If I go 4 times as fast, how much kinetic energy am I going to have? 16 times. So let's wrap up one thing on the formula here, and then we'll wrap up kinetic energy. Okay? So I told you that kinetic energy depends on mass and speed, but the formula says 1/2 mv squared, right? What did we say the difference was between speed and velocity from our 2 chapters ago? Velocity is a direction. That makes it what kind of a quantity, Kristen? It makes it a vector quantity. Now, energy isn't a vector quantity. If I'm going 30 miles per hour in a car one way versus 30 miles per hour in a car the other way, is that crash going to be any different? No. So, energy is a scalar quantity. Okay? But even if you look at the formula for kinetic energy, what are you doing to velocity in that formula? So even if you put a negative number in there, what's it going to come out as? If you square a negative number, it's a positive number, so it doesn't have direction. Okay? Yes?
What if both parts are going the same way? You know how like one person like.
Hold on to that question. We'll talk about that soon.
Okay.
All right. So one thing just to wrap this up. If you look at the calendar, there is no homework assignment on it just yet because yesterday I didn't have my book with me, so I couldn't put the homework assignments in. I'm actually going to do that right now, so if you check later on, we'll give you a little reading assignment and homework questions to go along with it. Okay? All right. Good job today, everybody. Pick it up there tomorrow.